Hello and welcome, my name is Kirsten Crane. I'm a computer science PhD student at Newcastle University in the northeast of the UK. I'm a member of Newcastle AI Lab working in the field of deep learning, but my project has a marine mammal conservation focus in collaboration with Dr. Per Begren of the Marine Megafauna Lab. As a multidisciplinary group, we are looking at ways to support cetacean monitoring with tech, both in terms of data analysis and in this case data collection. The Blue ROV2, which is the commercial remote operated vehicle we have, can be operated manually with a tether and game console controller. However, we are doing some early foundational research into cutting the cord between human and robot. Having the vehicle drive autonomously in such a way that it follows or perhaps just orients toward a species of interest is essentially a three-part task. The vehicle requires sensory data of some form, and in this project we consider visual data from the ROV's monocular RGB camera. In the context of active object tracking, there is then state estimation, so locating the target, and control. There are lots of different approaches one could take towards this goal, so for example state estimation could be achieved with animal tagging, and control could be achieved with something like a PID controller. However, in line with our interests and our expertise, this project focuses on deep learning as an approach. Again, there is more than one way to go about this. You could, for example, use a deep neural network for detection and then feed the bounding box coordinates to a conventional control algorithm, an approach which is not without challenges. What we are interested in is using deep reinforcement learning to combine the latter two steps and jump straight from perception to control, potentially offering a faster and more dynamic visuomotor control policy. In this approach, the output of the deep neural network is a distribution over some value range, for example the range -1 to 1 for each control dimension, for example steering and throttle. When training the network, there is an additional crucial component, which is the reward value for the time step according to a function designed and programmed by the researcher. An example of a reward function we have used issues a value between -1 and 1, scaled by distance from the optimal tracking position and the angular error in facing direction. Both of these measures are not known to the agent, or at least not without additional sensing technology. However, in a simulation of the real-world environment, these measures can be calculated from game object properties and utilised by the programmer to issue semi-supervision in the form of a reward signal. Simulations are also faster, cheaper and safer, and so are commonplace in robotics. The final component to the framework is pre-processing of the raw camera images. Prior to training the control policy with reinforcement learning, a deep neural network called a variational autoencoder is trained to reduce the images to a low-dimensional vector of features. This step reduces the search space for the RL algorithm and supports the sim-to-real transfer process. For more information, you can use the on-screen QR code, contact me at the on-screen address, or for in-person attendees, we hope to see you in the Group B poster session. Thank you.